Welcome back. We have another application. This one is over heat exchangers. We'll briefly talk about heat exchangers, then we'll have an example. A heat exchanger, in case you don't know, that's a device that allows heat from a fluid to pass to a second fluid. Now, the way this works is the two fluids don't come into contact with each other, but we still have the heat transfer that happens. And an example of this that everybody has probably seen would be the radiator in your car. So the radiator in your car is essentially a heat exchanger. It's going to transfer heat from that hot coolant that flows through it to the air that blows through the radiator. So you just exchange the heat. So the coolant then would cool down, and then that air that passes through it would get the energy from that hot coolant and it would warm up. So that's kind of a heat exchanger. They're also used in your HVAC systems, your refrigeration systems. They're found in a lot of different places. Now, in those devices, we're going to ignore kinetic and potential energy effects because we're not really going to pay attention to the velocity and we're not going to have an elevation change. So those will go away. We're going to stick with our same energy balance equation. This is going to be steady state. So we're going to have 0 equals Q dot minus W dot plus, if we assume multiple inlets and outlets, we'll have the summation over all the inlets of Mi dot times Hi minus the sum over the exits of Me dot times He. Now, if you think about it, the way this is working, this device, is you have heat transfer, but you don't need any sort of external power supply or anything to make this happen. This happens by the two fluids flowing next to each other. They don't come in contact with each other. They're going to be separated, but you can still allow that heat transfer. There is no external work or power that is needed though, so this goes away. Okay, so keep that in mind. So this will be our main equation. Now let's look at an example and we'll see how this works. We're going to have refrigerant. It's going to enter a condenser that's operating at steady state. Pressure is 70 psi, temperature is 160. It's going to be condensed to saturated liquid at a pressure of 60 psi on the outside of tubes through which cooling water flows. Now, in passing through the tubes, the cooling water increases in temperature by 20 degrees Fahrenheit and it experiences no significant pressure drop. Cooling water is going to be modeled as incompressible with a specific volume of 0.0161 cubic feet per pound, and we've got a specific heat of 1 BTU per pound degree Rankine. Our mass flow rate for the refrigerant is going to be 3,100 pounds per hour. We are going to neglect kinetic and potential energy effects as well as any heat transfer from outside of the condenser. Now, after all of that, we are going to find volumetric flow rate. Look at the units. It's in gallons per minute. It's kind of an odd unit. And then we're going to find the rate of heat transfer in BTU per hour to the cooling water from the condensing refrigerant. Lots to keep track of in that problem. So let's get started. Before we actually look at the picture, let's go ahead and look for our keywords here. We have steady state, which is good because this is what we had up here in this equation. We've got the refrigerant being condensed to saturated liquid, and our cooling water increases in temperature by 20 degrees. No significant pressure drop. The cooling water is modeled as incompressible. And then we're going to neglect kinetic and potential terms as well as heat transfer from outside. All right, so those are going to be our main things we need to pay attention to in addition to all these values that were given. Okay, and remember, incompressible, you remember what that means? It means density does not change. All right, so density will be constant throughout here. Now let's look at the picture. That'll make it a little bit easier. See what's going on. So here's the picture for this problem. So you can see we've got the refrigerant coming in here, gives us the mass flow rate, gives us the pressure, gives us the temperature. This is kind of blurry on the video. I can't get it zoomed in anymore though. And then as the refrigerant comes in here into the heat exchanger, we've got these, or this one tube here that wraps around. This is going to have cooling water flowing through it. Now the cooling water enters over here at A, it exits at B. There is a temperature increase of 20, and then we've got pressure. Pressure is going to stay the same between A and B. Now the refrigerant, it comes through here. Notice it's in contact with these tubes, and then it exits at exit 2. Pressure is now at 60, and it's saturated liquid. All right, so that's kind of how it works. The refrigerant basically surrounds these tubes, and then there is heat transfer. So let's go ahead and we'll work through this problem, and we'll kind of explain what's going on as we go through it. Now, first of all, we've got two substances here, so we're going to have to look at mass flow for both of the substances. Let's start with the refrigerant. We're at 0.1 for the entrance, 0.2 here for the exit for the refrigerant. And we have steady state conditions. So M1 dot, it's got to equal M2 dot. Let's just call it MR dot. So we know that this is for the refrigerant. Right, so that's for the refrigerant. And then for the water, we need to look at that. This is also going to be steady state. The mass flow rate at A is going to equal the mass flow rate at B. So we have MA dot equals MB dot, and let's just call it MW dot. This will be for water. Now, let's go ahead and write down our energy balance equation. Now remember, we've got two different substances, so our equation has to account for both of those substances. We're going to have 0 because it's steady state equals Q dot minus W dot plus, let's do the refrigerant, MR dot times H1 minus H2, because that's the entrance, then the exit. Then we're going to have plus MW dot times HA minus HB. So that's what we end up with. So we have to have both of the fluids in there because both of those are entering into the system, so they're all going to contribute to that energy balance equation. What we are looking for, remember, is the volumetric flow rate of the cooling water. Keep that in mind. Remember, that's AV. All right, so that's what we're looking for. Let's go ahead and solve this equation 1 right here. Let's solve it for the mass flow rate of water. Again, we're going to do that because we're looking for volumetric flow rate of the water. And M dot has AV in it. So let's solve 1 for MW dot. If we do that, we get the mass flow rate of water is equal to negative MR dot times H1 minus H2 over HA minus HB. So that'll be our equation. Now we've got that. Now MR dot is given to us, right? It's up here, it's 3100. The units there are pounds per hour. So with that being known, we can plug that in, and then if we can find these H values, then we can find the mass flow rate of water. So now let's look at finding the enthalpy values. We'll start with H1. That's the enthalpy value for right here, the entrance of the refrigerant. We know the pressure, we know the temperature. So we need to look that information up in our tables. Let's go to our table and we'll look and see what we have up here? We know at exit, at this point, we have saturated liquid, so that one's easy to know what table. Let's look and see what we have here. You should be able to tell, but just to show you how to go through the tables and figure it out, let's look at it. Let's look at our pressure. The pressure is 70, so go to your saturated refrigerant table, find 70. Saturation temperature is 58.13. Our temperature is way above that. That's 160. All right, that means we need to go to the superheated vapor table. And if you do that, and you look at your pressure temperature combination, here is 70, here's 160. H is going to be 133.82. Let's write that number down. And that unit there is BTU per pound. After you do this enough times, eventually you won't really have to look at that table to figure out if it's superheated vapor or not. You'll just know, but I always just show y'all anyways, just so you know where everything comes from. And that was from table A12E. Now, if you do the same thing here at the exit for 2, for this point, we know we have saturated liquid. We just need to look in the saturated table to find our H value for that specific pressure. All right, so we're at 60. So come back to this table, look at 60, and then if we have saturated liquid, then we're going to come over here till we get to enthalpy, and we're going to be right here, 27.24. Notice that's saturated liquid. That's that F point on that vapor dome. All right, so we write down 27.24. It's BTU per pound, and that's from table A11E. Now we got that figured out. The cooling water, we need to find HA and HB. If you look, we're not given really any information about pressure. We have no idea what the pressure is. We just know pressure at A equals pressure at B. That's all we know. We do know, however, that the specific heat is 1 BTU per pound degree Rankine. Remember, we have equations we can use to find enthalpy if we have specific heat. HA then is going to be C times the temperature at A. And then HB would be C times the temperature at B. Now we have that we can use. And in our equation, we want to find HA minus HB. Let's write it out here. We can pull C out because that's the same. We'll have C times TA minus TB. C is 1 BTU per pound degree Rankine. And we want to multiply that by negative 20 degrees Rankine. Now if you simplify all that, you'll get HA minus HB equals negative 20 BTU per pound. We have everything we need now to plug into this equation. Let's do that next. Let's call this equation, well, actually not 1, let's call it equation 2. This is the word from here. It's hard to tell what that is, but that's what it is. Now, the mass flow rate of the water is going to be negative 3,100 pounds per hour. That was the mass flow rate of the refrigerant. We're going to multiply that by H1 minus H2. That gives us 133.82 minus 27.24. Units there are BTU per pound. Multiply it by 1 hour per 60 minutes. And I'm putting it in minutes because we want volumetric flow rate to be in gallons per minute. So let's go ahead and convert over. Then we divide by our HA minus HB, which we already said was negative 20 BTU per pound. Now let's look at our units here. So our hours are going to cancel out, so that's good. And what else are we going to have here? BTU cancels, and then this pound cancels with that. Now if you look, we still have pound down here on the bottom. So our units will work out. We end up getting 275.33 pounds per minute. This is our mass flow rate for water. We know this has to equal volumetric flow rate for the water over the specific volume. Now let's go ahead and find volumetric flow rate. If we solve this for AV, we're going to get AV equals mass flow rate of the water times V. And mass flow rate of water we just found 275.33. So let's plug that in. That was pounds per minute. Our specific volume, do we need to look that up? Nope, it was in the problem. That number is the 0.0161 number that was given. That's cubic feet per pound. And remember, we want to get this in gallons per minute. We don't have gallons anywhere in sight here, so let's do the conversion. The conversion between gallons and cubic feet is 1 gallon per 0.13368 cubic feet. Now make sure your units all work out. Pounds is gone now. Cubic feet gone. Leaves us a gallon per minute. Multiply your numbers. And your volumetric flow rate for the water is going to be 33.16 gallons per minute. Okay, so that is your volumetric flow rate for your water. Pretty interesting, right? Pretty cool stuff. Now let's go to part B. We're going to find the rate of heat transfer to the cooling water from the condensing refrigerant. So on B, what we're going to do here is, in this one, we are going to look at just the water. And the reason for that is because we want to isolate the heat transfer to the water from the refrigerant. Up here, notice we had both of these substances in here. Our control volume, which I forgot to mention, it was essentially this whole thing. All right, so the whole thing was the control volume. And that's why we were able to put both of these in here. Down here, we want to isolate the cooling water. So the cooling water, let me just draw a box here. It's going to represent the heat exchanger. And then we've got this tube, looks like this. Our control volume now is essentially going to be this tube that carries the cooling water. And we're going to do that because we want to isolate the heat transfer. So let's write our control volume will be the cooling water tube. Because again, if we had this whole thing in here, if we did the whole exchanger, our Q dot term would be the total heat transfer. We want to isolate it, so we only want to look at the cooling water. Now for our equation, we're going to have the energy balance equation, steady state still, so we still have 0 on the left. That's going to equal QCV dot minus W dot plus flow rate of water times HA minus HB. Now, are we going to have a W dot? Remember, W dot is like an external power or rate of work. We don't have that, right? We don't have any shafts turning. We don't have anything plugged in, nothing like that. All of this happens on its own just due to the contact of the refrigerant with this tube carrying the cooling water. that means that goes away, so we can solve for Q dot, and we'll get a negative mW dot times HA minus HB. Now we have that. We have mW dot. We found that up here. We already found HA and HB. Those were right up here. So we have all of the values that we need to find Q dot. We just need to plug in our values. Now if we plug it in, you get negative 275.33, that's pounds per minute. Multiply that by the negative 20 BTU per pound, and let's get this in hour because it wanted the units to be BTU per hour. Conversion for that will be 60 minutes per hour. If we look at our units, minutes goes away, pounds goes away. That leaves us with a Q dot of 330,396 BTU per hour. All right, so now we have that. Now look at the sign here. This is greater than 0. All right, it's a positive number. That again shows that that is the heat transfer to the cooling water. All right, so let's look at what happened to our temperature of our refrigerant. Basically, our temperature, we wanted to cool it down. Now, we saw what happened to the temperature of the cooling water. So the temperature at B minus the temperature at A, that was equal to 20. So that means the temperature of the cooling water heated up by 20 degrees. Pointing up here, you guys can't see. So it increased by 20 degrees. Now that increase in temperature had to come from somewhere, and where that came from was this hot refrigerant that was coming through this heat exchanger. Now let's look at the temperature change for the refrigerant. We started out with a temperature of 160 degrees Fahrenheit. We weren't given the temperature here at the exit, but we do know we had saturated liquid. So if we had saturated liquid, we can find the temperature in the table. So if you go to the table and then you look up the temperature, let's put refrigeration temps or refrigerant temps. So T1 was 160. Now again, what we wanted to happen was this temperature to decrease. So T2, if you look up the value for the saturation temperature at a pressure of 60 degrees in your liquid vapor table, here we got our pressure of 60, and here's our temperature. So 49.89. So T2 should be 49.89 degrees Fahrenheit. Now you can see there was a pretty big decrease in temperature, and all we essentially did was run this tube of cooling water through this heat exchanger. And then the hot refrigerant was in contact with the cooling water, so there was a heat transfer. And we basically used that cooling water to remove heat from the refrigerant. And we showed that by looking at this positive number here. It's positive, so whenever we have a positive Q value, we're going to have heat transfer to something else. So here, it was heat transfer to the cooling water. All right, and all of that was happening without any sort of need for a power supply or anything like that. All right, pretty awesome stuff. I'll see y'all in the next video.